Excellent. Thank you. Thank you so much, Alex, for the invitation. This really is a privilege. I think I've been to all of the BBLOC seminars, or back in the day when it was just a block seminar, and the talks have just been uniformly excellent. So it's an absolute privilege to have been invited here. So thanks a lot, Alex, and Simon as well for helping to organize this. It's in a sense doubly a privilege to talk about what I'm going to be talking about today, because it's based on today's talk is based on a paper that I wrote with Nick Huggett and Fidele Lizzi. And I was in the odd position of being invited actually to contribute to a paper, which was itself the paper that stimulated my interest in the topic. And you don't really find yourself in that situation very often. You don't run into Russell saying, I've got this draft of on denoting, would you like to add something to it? But that's sort of what happened over here. Nick had this draft floating around. Decided not to use it in his book, and then Fidele and I sort of added our own little bits to it. If you did see Nick's talk at the Thursday seminar a couple of weeks ago, you might recognize some of this material, but this is intended to be a standalone talk, and in many ways complementary to the things that Nick argued for. The paper itself is kind of long and involved, so there's much that sort of sprouts out of it. As I said, I'm happy to be interrupted for clarificatory questions or updates on the cricket or really anything. But yeah, let's crack on. I hope all of my slides and everything are working. Right. So as I said, the focus is going to be very slightly different from Nick's focus. As the title suggests, it's going to be a bit more metaphysically oriented, and that will come towards the end of the talk. I should also say that's not the full title. This is the proper title that I wanted to give the talk. But anyway, Simon's precluding my puns notwithstanding, let's go. So let me, at the outset, tell you what I hope the take-home messages from this talk are going to be. And there are two sort of prima facie unrelated take-home messages, which hopefully by the end will sort of coalesce appropriately. The first is a slightly more general conclusion to the one that Nick had a couple of weeks ago. And so I want to say, when physicists or people who think about non-commutative geometries in general make the claim that there are no, you're ontologically committed to a geometry with no arbitrarily small areas, then you're on solid philosophical grounds. It's not one of those sort of throwaway comments that sort of crumbles under examination. And the way that I want to argue for that is by actually talking about this notion that metaphysicians have been discussing for quite a while, known as metaphysical indeterminacy. And I think that's a useful lens to assess non-commutative geometries and their claims. And conversely, I think non-commutative geometries are sort of a nice playground for counterexamples to particular claims from the metaphysics literature about metaphysical indeterminacy. So I want to sort of bring these two bits of the literature into contact with each other. So to that end, the plan of the talk is fairly straightforward. It's going to be in 3 sections. I'm going to spend a little time on motivations, because I think if you're discussing stuff that's kind of non-canonical in the discipline, it's probably worth spending a few minutes talking about why we should care about this. Why should I care about the ontological commitments of non-commutative geometries if they don't really tell me anything interesting about the actual world? I'm going to set up the motivations in such a way that sort of naturally leads to me introducing at least some of the important moving parts in non-commutative geometries. It's not going to be very formal. It's not going to be very technical. I'm really just going to try to highlight some of what's conceptually interesting and kind of sort of underexplored from the perspective of the sort of field theories that we know and love. And then, having set all of that up in the last maybe 20 minutes or so, I'm going to discuss some proper metaphysics, or at least metaphysics as proper as I can make it. So let's So let's go ahead. Now, discussing motivations in general, I think you're sort of very firmly in kind of context of discovery territory. So you're never going to get anything that's going to convince everyone. You're never going to get a theorem that says, this is the reason why you should care about this. So what I'm going to do is I'm going to focus on sort of 2 broad sorts of motivations. The first coming from a kind of more generic philosophical consideration to do with generalizations. And the second coming from a more physics-oriented, look at me recording at that font, physics-oriented direction to do with unification and sort of the heuristic force of unifications in physics. So, there's good reason to interested in generalizations of physics that we take to be well established, right? On purely conceptual grounds, even if it doesn't lead to any kind of new physics, what it does is it highlights, some of the contingencies that you might not have thought of as being contingent from within the structure of your physics. And I think there was a really nice quote from a book, from a very underrated book by Max Born on Einstein's theory of relativity. I mean, ordinarily we all associate Max Born, we know Max Born from a totally different context, right? As famously the grandfather of the actress Olivia Newton-John. But he was also a good physicist. And here's a line from that book. I promise this is the only chunk of text that I'll be giving you. And he says, "It is nothing more than a thought habit when an idea impresses itself so strongly on minds that it is used as the ultimate principle of explanation." I should say that he's saying this in the context of action at a distance force theories like Newtonian gravitation. It does not then take long for metaphysical speculation, often in the garb of philosophic criticism, to maintain that the correct or accepted principle of explanation is a logical necessity and that its opposite cannot be imagined. And so I think he's saying something I think a lot of us can agree with, especially if we're in particularly sort of acerbic moods towards our colleagues. The idea is, we've learned in the past that things that have been taken to be, for example, a priori or whatever, have in fact turned out to be not only not necessary, but also, or not a priori, but also in fact false. And I think the motivations for looking at non-commutative geometries from that perspective are sort of fairly clear and straightforward. So that's really all I'm going to say about motivations coming from generalizations. The second kind of motivation comes from the sort of, as I said, the heuristic force of unifications in physics. And the basic thought over here is something that a lot of people have discussed in, it was certainly an active area of discussion in the early to mid part of the 20th century when talking about unified field theories in the hands of people like Weil and Einstein and Kaluza and Klein. The thought was, if you can suitably generalize your geometry, and of course the word suitably is doing a lot of work there, you can effect a unification between theories of matter or theories of forces and theories of gravitation. And in particular, if you've got things like what you might think of as material degrees of freedom and gravitational degrees of freedom, then there's at least a hope that that you can effect a unification such that these degrees of freedom are associated in some sense with the same object. And it's a unification along the lines of how you unify electricity and magnetism to give you electromagnetism. Of course, it doesn't mean that the electric field is identical to the magnetic field. It just means that they're manifestations of the behavior of the same object. And so with that unification in mind, you might think, okay, let's see if we can talk about something like a pure gravitational dynamics in some perhaps higher dimensional space or some space with different geometrical features, which reduces to a theory of interactions between gravity and matter in lower dimensions. And this kind of thinking, this kind of reasoning can be wholly classical. And in fact, in this talk, I'm only going to focus on the wholly classical aspect of this kind of reasoning. I should say, there are ways in which you can sort of straightforwardly generalize this to talk about quantum theories, but I'm not so interested in that, at least in the body of this talk. So what is the kind of, this bigger should be in scare quotes, right? What is the kind of bigger manifold that can affect a unification? Well, I alluded briefly to this idea of Kaluza-Klein, and the basic idea, and of course there's a lot more to be said about this, but as I said, context of discovery, so I can be a bit hand-wavy over here. The idea behind Kaluza-Klein theories is to say, if you look at the Einstein field equations, the vacuum Einstein field equations in 5 dimensions, then they govern the dynamics of an object that can be that encodes all of the information about a 4-dimensional gravitational theory interacting with electromagnetism. So that's a kind of unification that I think a lot of people think of as being sort of fairly straightforward. You've got a 5-dimensional metric that unifies gravity and electromagnetism. And so now you might ask the question, well, can we do this for things more complicated than electromagnetism? In particular, can we do this for the standard model symmetry group? And it turns out, depending on whom you ask, that the answer is yes or yes star. And the yes, the star is a bit of is the caveat. And the caveat is that unlike in the case of Kaluza-Klein, where everything just increases in dimension, but everything remains kind of good standard differential geometry manifoldy. What happens when you incorporate the non-abelian symmetry groups of the standard model, in particular SU2 and SU3, you end up with a kind of non-abelian character in your geometry. And that's what goes on, that's what we generally, in a generic sense, refer to as a non-commutative geometry associated with space-time. So at this point, we, I think, have two choices. We can say, well, we tried to generalize it, and we ended up with this nonsensical idea of a non-commutative manifold. I have no idea what sense we could possibly make of this. We tried, we failed, let's move on. Or we can say, well, no, this is pointing towards a sensible way in which we might be able to generalize some of these ideas, some of these geometric ideas that have been so successful in the past. And so it's the second choice that I'm going to use to define the project, the sort of overarching project of non-commutative geometries, which is to try to characterize generalizations that need not necessarily actually be non-commutative, but to characterize generalizations of the familiar sorts of geometric structures that we use in our favorite physics, and then kind of deform them and poke them and prod them and break them and see, see what happens. And that's what I'm going to do in section B. So that's really all I wanted to say about motivations. Hopefully the motivations have also set up the manner in which I'm going to introduce the project of non-commutative geometries in the next section. So as always, I think it's useful to just have a sort of really basic question in the back of your mind when going through material like this. So the basic question is, how can we make sense of something that you might call a non-commutative geometry? And the answer is, or at least an answer is, let's see if we can find a formalism that's going to spit out things that are extensionally equivalent to differential geometry when we're in the domain of differential geometry, but which doesn't break when you sort of appropriately deform it in a way the differential geometry appears to break. And so we can say, all right, fine, that seems sensible. Where do we begin? And I think a good place to start is by looking at how we characterize things like smooth manifolds via talk of structure preserving maps. Like, so in the case of smooth manifolds, it would be diffeomorphisms. So again, let's ask a really, really basic question. What is a diffeomorphism? And, pick your favorite differential geometry textbook. I'm pretty sure I can do this without looking. Maybe not. There we go. I did get my favorite differential geometry book. And if you look at a book, if you look into a book, you thought this was just a prop, didn't you? It's not. It's not a Zoom background. It's real. If you look at a book like that, the sort of standard answer that you'll get is something like a diffeomorphism is an isomorphism of smooth manifolds. You go, brilliant, what's a smooth manifold? And you're generally given a characterization in terms of transition maps, in terms of restrictions on transition maps between coordinate charts. And so the notion of a coordinate chart or a coordinate system is playing a really central role in our conceptual understanding of what's going on with manifolds. So let's sort of hone in a little bit on our coordinate systems and really ask the question of what sorts of mathematical objects they are, and what sorts of sort of contingent facts about particular choices we might be able to sweep away. So at its most basic, in its most simplistic form, a coordinate system is just a function from some manifold, or perhaps some submanifold of a manifold, into the real numbers, into a tuple of real numbers. I'm going to focus on 4-dimensional manifolds for now, but more generally, it's going to be Rn. And we know from, I guess, maybe first or second year linear algebra that if you've got a space of functions such as this, then it forms a vector space. You can take arbitrary linear combinations and stay within the space. And so really what you've got is, when you're talking about coordinate systems, you can just as easily talk about a space of smooth valued functions as a vector space. But of course, since these smooth valued functions are valued in, since these real valued smooth functions are valued in the real numbers, and the real numbers have more structure than that, we can actually define a pointwise algebraic structure and turn this space of smooth functions into an algebra. And that's going to turn out to be extremely useful. And that's really going to be the kind of central formal move that we're going to be making when talking about NCGs. And the way to see how this is going to allow us to be a bit more general is to focus on a sort of notational ambiguity that I think a lot of us have bashed our heads up against in the past. And that is a notational ambiguity when you're presented with a term like this. So generally, this is thought of as, this is the x coordinate or the x mu coordinate of some point P on a manifold. The question is, am I supposed to read this as sort of the actual value of that function or the function more generally. And so to disambiguate, you can think of x mu as representing just the whole function, the function evaluated at every point on the manifold. And you can think of x mu at P as just the evaluation at that point P. So these are two different objects. But in sort of ordinary, under normal circumstances, context really determines which of these two things you're talking about. So it doesn't really matter. Apply the principle of charity and everything will be fine. But what this sort of points to is a kind of intuitive idea that the function is determined by just evaluating, by just sort of collating these values at all of the points in the manifold. So if I know the x mu for all of the p's, then I just know the x mu. But notice on the previous slide, I said you can also think of these x mu's as elements of abstract algebras. And so in its capacity as an element of an algebra, you don't need to say anything about it being valued on a manifold or anything like that. All I need to give you is the algebraic relations that this x mu stands in with respect to all of the other elements of that algebra. I never have to mention a manifold at all. And so now I can start with an abstract algebra, which now I'm just going to characterize, which now I'm just going to denote by this fancy curly swanny looking A. And if I just give you a fancy swanny A, what I can say is, look, it's got some algebraic properties. A certain subclass of these swanny A's will be such that I can interpret each of these elements as functions on a manifold. But more generically speaking, I don't have to do that. I can just talk about the algebraic structure of swanny A. I have to stop saying swanny A, so that was not intentional. And now we can ascribe the property of commutativity or non-commutativity directly to the A, and we can just say A is commutative if and only if for all of the elements of A, the commutative vanishes, right? AB minus BA equals 0. There's an if and only if, so non-commutative is just a non-commutative algebra is one that just doesn't satisfy this criteria. Great. So now let's focus on the abstract algebra of, well, let's just call it the abstract algebra A. If A is commutative, again, there's a little asterisk there because there are a few more sort of technical requirements that need to be satisfied, but I'm going to elide past all of them. If A is commutative, then there's always going to be a unique manifold M such that if I give you this A, you have this little black box that you can chuck A into. And what that's going to do is it's going to associate with each element of A function, a smooth function on some manifold. And it's going to do this uniquely. What I mean by that is for two distinct non-isomorphic A's, you will always be led to the set of smooth functions on two non-homeomorphic manifolds. So there's a one-to-one correspondence between structures encoded in the algebra and structures encoded on the manifold. Right? So the manifold structure is incorporated into the algebraic structure, but not in a very direct way. There's nothing that you can point to directly in the algebra. There is some, there's a certain algorithm that you have to hit it with, and then it spits out a manifold. And so you go, okay, brilliant. Well, it spat out a manifold. I've understood manifolds so far in terms of diffeomorphisms and structure preserving maps. So is there some way that I can talk about diffeomorphisms on the manifold associated with this algebra? But in purely algebraic terms, not having to use the word diffeomorphism or manifold. And the answer is yes, there's a class of automorphisms, right? Structure preserving maps from the algebra to itself that stand in a one-to-one correspondence with all of the diffeomorphisms that you can impose on the manifold M. And so now you think, okay, well, this is great. We've kind of got a surfeit of different descriptions. It's always nice when we've got a surfeit of different descriptions because we can then really use it to test various kinds of metaphysical claims. And so the proposal is to treat the algebra as, I don't want to say fundamental in any particularly sort of stringent sense. It's just sort of basic, just more basic formally than any kinds of geometrical claims. And by geometrical claims, I just mean claims about stuff that you can define on smooth manifolds. So things like tensors and vector fields and the like.
Tushar, can I just ask a very quick question, clarificatory question? Are you assuming that the manifold M is covered by a single chart when you set these functions, these scalar functions, these coordinate functions, and so on? Or no? Or is that there no such underlying?
So for expository purposes, I'm making a lot of assumptions. Yes, I'm assuming it's covered by a single chart. I'm going to also assume that it's compact. But there are generalizations, there are sort of further restrictions that you can add in such a way that you don't have to worry about things like global charts and compact manifolds and the like. But in the interest of dialectical simplicity, I'm making these assumptions. But yeah, you're absolutely right. In the way that I've set things up, we've got a global chart, but that doesn't need to be the case.
Okay, thank you.
Yeah, right. So the proposal is sorry. So the proposal is we start with the algebra, and then we look at the kinds of geometrical objects. This is not geometrical objects, and of course, in the sort of very specific Friedmanian sense. More generally, the sorts of objects that we talk about when we talk about geometries. So now the proposal is, as I'm saying for the fourth time, we treat the algebra as fundamental. I see something about Gelfand and Neimach. That is exactly what I'm invoking here. But anyway, sorry. So we've got this algebra manifold correspondence perfectly straightforwardly, at least as far as smooth structure goes. And now what we can do is we can break this correspondence by dropping the commutativity constraint on the algebra. But in doing this, it doesn't mean that we can no longer talk about automorphisms on the noncommutative algebra, right? All that we said about defining automorphisms carries forward perfectly well to the noncommutative case. And so now, if we return to the question, what is a diffeomorphism, we can give it a wholly algebraic, commutative algebraic characterization. We can say it's an automorphism on the algebra of functions. And then we can talk about something like a generalized diffeomorphism as just being an automorphism on that algebra. And we can therefore talk about quote unquote diffeomorphisms without being committed to manifolds of points. And so you go, okay, fine, that's a nice bit of mathematical magic, a bit of mathematical sleight of hand. Can we actually do any physics with this setup? And of course, if all we needed in order to do our physics was just smooth structure, then the answer would be, of course, yes, because we've got this straightforward bijection. But we generally need a lot more to do even the most basic kind of physics, right? We need things like tensors if we want to do relativity theory and Newtonian mechanics. We need connections. We also need things like actions if we want to incorporate things like least action principles and various other things, right? This is not intended to be an exhaustive list. So now, in terms of what I've presented to you right now, we can say, okay, the algebraic characterization can give us manifolds, can give us differential operators. I sort of slid that in by just directly talking about smooth structure, and it can give us scalar fields, right? Those are the functions that I've talked about. Robert Garot showed us in a brilliant 1972 paper how we can do all of GR, because you can also incorporate tensors and connections and all of the other things and integrals and all of the other things that you need to do GR. So we can certainly do a theory as complicated as general relativity in purely algebraic terms. And so this points to the game that we have to play, right? The game is identify the requisite mathematical objects, recast them in algebraic terms, check if the physics breaks. And the physics might break in unexpected ways, right? It might, for example, turn out that you can't define an action. Of course, it turns out if you drop the commutativity relation, that doesn't happen. So the actions are fine. So if the physics doesn't break, you rejoice, and then do a little bit of metaphysics. And so that's what I'm going to be doing today. And the example that I'd like you to have in the back of your minds, I'm not going to talk about this explicitly, is something like the equivalent of a Klein-Gordon theory, a free Klein-Gordon theory, but for a non-commutative space. So if I want to talk about a theory like that, I'll need scalar fields, I'll need differential operators, I'll need actions, and I'll also need a metric. And I haven't said anything about metrics so far. So let me spend a few minutes talking about metrics, and that'll bring this section to a close. Now, in general, what does a metric do? Sort of intuitively, you look at a set, it looks at all of the pairs of points in that set, and it spits out a real number. And those real numbers have to behave in such a way that they sort of intuitively capture the idea that we've got something like a distance, right? Triangle inequalities and the like. So if we want to talk about the algebraic characterization of a metric manifold, then we're going to need to add a little bit more. We're not going to get that directly from the algebra itself. The other reason that I wanted to talk about metrics is looking ahead to what I'm going to discuss in the last section. I'm going to want to talk about localizability in metric rather than topological terms. I'm not going to justify this, but I'm happy to talk about this in the Q&A. And in particular, I'm going to think about localizability. I'm going to think about arbitrary localizability in terms of our ability to define arbitrarily small spatial separations. So now the question is, can I define arbitrarily small spatial separations algebraically? Which is, of course, a special case of the more general question about whether we can define metric manifolds algebraically. And the answer is yes. But it's yes at the expense of, as I said, introducing a little bit more structure. And we can see how to do this by taking a cue from the way we ordinarily do metrics on manifolds. So how do we ordinarily ascribe distances to points on a space where we can't just sort of list out the distances associated with the pairs? It's straightforward, right? You connect the points with an arc, you break that arc into infinitesimal, into line elements, and then you integrate over it. I was very pleased to discover that I could animate things on Keynote. So this is a completely gratuitous animation of what goes on when you want to figure out the distance between those 2 points, P and Q, along some curve gamma. If you want a geodesic distance, you just take the infimum of all of those integrals, and that's going to give you the shortest distance between P and Q. And so that's how we're going to get. That's how straightforwardly you get spatial separations on manifolds.
Tushar, could I ask you a question?
Of course, Jeremy.
Yeah. How much is today's talk or the whole program limited to requiring non-Lorentzian signature? How much are we, as regards the classical NCG you're confined to, how much are we really talking about Riemannian manifolds?
Yeah, so today exclusively, and indeed even in Nick's talk 2 weeks ago, exclusively non-Lorentzian. These are intended to be sort of toy models for a sort of non-relativistic non-commutative theory, indeed a non-relativistic non-commutative spatial theory. But I mean, I'll sort of outsource the more general answer to Fidele in the Q&A, but there are a lot more realistic models of these non-commutative geometries that do incorporate, and in fact, do incorporate it via these the spectral triples that I'm about to introduce right now. So think of this as, sort of dialectically slightly more straightforward stepping stone, but these ideas will carry forward. These ideas are not going to be broken by the move to Lorentzian or to considerations of things that reduce to Lorentzian manifolds going forward.
Okay, thanks.
So right. So we know how to talk about spatial separations and indeed arbitrarily small spatial separations on manifolds. And now the question is, as I've repeatedly said, we've got this algebra manifold link. Can we do fancy things with the algebra? And the answer is yes. And it's a two-step procedure for the algebra. The first step is what we've already done. We want to establish a bijection between manifold points and something that you derive from the algebra, right? Recall that I said something like, give me an algebra, chuck it into a black box, and it'll spit out a manifold. So that black box is deriving something from this algebraic structure. And in particular, what it's going to do is, at least for commutative theories, it's going to establish a bijection between manifold points and some structures. What is that structure? Well, that structure is actually the space of what are known as pure states. I'm not going to go into the definition of what a pure state is. It's sort of very much, it's precisely what we refer to as pure states in the quantum context as well, but it's something that you can define given absolutely any algebra. Restricted in the ways that I'm restricting it in this talk. And so there was a paper, I think in the early 40s by Gelfand and Naimark, where they established this this homeomorphism between the space of pure states associated with some algebra, with some commutative algebra, and a manifold. And so with that, equipped with that, we've got as I've already demonstrated, a link between manifolds and algebras. The question is, how do we add metric structure to this? And the answer is, we want to establish a correspondence between geodesic distances on the manifold and something in an algebraic structure. This is how we got the geodesic distance on the manifold. What we need to do is define something that's numerically equal to the dp to the distance between p and q, but is defined on these objects a and b, which are elements of the space of pure states. So if we can always establish that given some points p and q in a commutative manifold and some distance between them, I can always find a corresponding distance between two pure states defined on the algebra of functions over that manifold, then I've got a purely algebraic characterization of metric structure. Notice that at the end of the bracket, I don't know if you can see my cursor, I assume you can't, but notice that right at the end, towards the right-hand side of that bracket, there's an object D, and there's some norm over there. So that object D is this new structure that you need to incorporate. It's known as a Dirac operator. And for the purposes of this talk, it's just some new piece of structure that you need to incorporate. And if you have that piece of structure, then you have enough to define the notion of an algebraic notion of a metric that corresponds precisely to the Riemannian idea of a metric that we know and love from the definition that we already have. So as I said, step 1 only requires the algebra. Step 2 requires the Dirac operator as well. In fact, it requires a little bit more. It requires a Hilbert space on which we can represent that algebra. But once we've got these three things, we've got what's known as a spectral triple. The spectral triple will consist of some algebra that may or may not be commutative, some Hilbert space on which that algebra is represented, and a Dirac operator, which for now is just a black box that encodes this, a particular metric structure. And now spectral triples will allow us to characterize metric manifolds algebraically. And in particular, every metric manifold is always going to be associated with a commutative spectral triple. But of course, you can see where I'm going with this. We drop the commutation requirement. We can still talk about a generalized idea of metric structure. And that's what we're going to do. But that brings me to the end of section B. So let me briefly summarize. I feel like I've said this a lot, but the project was figure out what maths we need to write our favorite theories and express those mathematical structures in an algebraic form. We saw that every commutative algebra can be associated uniquely with up to diffeomorphism with a manifold. So if we've got purely manifold-based physics that we want to do, we can do it in terms of algebras. If we want to do slightly more realistic physics, we have to be as good as Garroch, which I'm not. So I invoke his descriptions and definitions of things like tensors and connections and the like. Garroch demonstrates that those can be given algebraic characterizations. And I think the sort of lesson to derive from this is a sort of broadly what I would think of as a kind of Russellian lesson, which is don't be fooled by the surface grammar. In this case, the surface grammar of our physics, right? It seems like in order to write down general relativity, we needed that manifold of points because we couldn't define tensors and vectors and integrals and the like without that manifold of points. But it turns out that if we just, in a counterfactual universe in which we were sort of algebraically more sophisticated, we discovered the algebras first, and the surface grammar of that kind of theory looked very, very different, and we would presumably derive quite different metaphysical conclusions from that kind of, from that form of setup. So now, as I said, we've equipped ourselves with an algebraic characterization. We drop the requirement of commutativity. Good. So that's basically all I wanted to get on the table about non-commutative geometries. I've got another. I'm actually doing quite well for time. Sorry, shouldn't sound so surprised there. Anyway, that gives me plenty of time to talk about what I wanted to do with respect to metaphysics. So I think apart from everything else, it means I can talk a little bit more slowly. Let me remind you of the take-home messages that I hoped to impart, that I mentioned right at the beginning of the talk. The first was the claim that you're on perfectly respectable philosophical grounds when you make the claim that there are just no arbitrarily small areas in worlds that are governed by non-commutative geometric physics. And then the second was a broader claim about how we can use cutting-edge physics or whatever to derive, I think, quite useful lessons about just sort of pure metaphysics. Okay, I'm going to use these two take-home messages to kind of structure the last part of this talk. So the first half of this last section is going to be about metaphysical indeterminacy and a sort of a semantic idea of definability, and that I'm going to use to argue this claim about points in NCGs. And then I'm going to sort of assess the conclusions that I come to. I'm going to have what I call a weak conclusion and a strong conclusion. In some ways, the strong conclusion is a subset of the weak conclusion, but I'm thinking of this more as a sort of a weak conclusion in the sense of a weak-willed conclusion versus a strong-willed conclusion. I suspect that'll get me into a bit of trouble towards the end of the talk, but anyway. So let me briefly introduce you to a section of the kind of metaphysical literature from the last, I guess, maybe 40 or 50 years. There's been this debate in the literature associated with people like Lewis and Evans, and then more recently with people like Jessica Wilson and Elizabeth Barnes, about whether or not there's some distinctively metaphysical notion of metaphysical form of indeterminacy. By indeterminacy, I just mean something like vagueness or indefiniteness or kind of fuzziness. These are all the sort of hand-wavy ways of sort of pointing to an intuition that some metaphysicians have. And the idea is, look, we're quite used to things like semantic vagueness or semantic indeterminacy, right? The standard example is something like, what is the extension of the predicate is bald? And proponents of semantic vagueness will say, well, there are going to be some valuation function, there are going to be some structures on which the predicate is bald is satisfied by particular objects, and some structures on which it's not satisfied. And there's no matter of fact as to which of these is sort of the true, gives us, so to speak, the true extension of the predicate is bald. And so this points to a kind of deficiency, a sort of semantic deficiency. And the idea is, well, that's a distinctively semantic deficiency. Perhaps there's a kind of epistemic version of this. There's a sort of deficiency in our knowledge of the world. And there are some people who think, well, there might just be some deficiency with the world itself. There might be some properties that particulars in the actual world might instantiate, but in fact don't determinately instantiate. So another way of thinking about metaphysical indeterminacy is it's the indeterminacy, or the fuzziness or the vagueness. I'm going to use these terms interchangeably. It's a residual indeterminacy after you've removed all of the semantic and the epistemic indeterminacy. So supposing there is the kind of most precise language that we could possibly have, and we've got our description in terms of that language, and we've got all of the sort of the most precise knowledge that it's possible for knowers to have with respect to that language and that possible world. There might still be facts that are not determinate with respect to certain properties in the actual world. And if there are such facts, then there's metaphysical indeterminacy in the actual world. And so notice I've used terms like I don't know if I've actually said unsettledness. Unsettledness. So notice I've used terms like unsettledness and fuzziness and vagueness. But I think we should tighten this up a little bit. And I think a good way to tighten this up is to invoke I think some very interesting work done by Barnes and Williams in a paper where they choose to model metaphysical indeterminacy as a form of modality. Now, it's not a reductive analysis in the way that a lot of analyses of modality itself are not reductive. And what they say is we should think about metaphysical indeterminacy as a form of modality in the sense that we can introduce what they call precisificationally possible worlds. I don't think I'll say precisificationally possible a lot because it's a bit of a tongue twister. I'm going to keep saying PPWs. Now, a PPW is just, for Barnes and Williams, it's a maximal and classical ersatz possible world. So let's go through those terms one by one. Ersatz possible worlds are just in contrast to things like Lewisian possible worlds, sort of concrete possible worlds. These are just abstract constructions. Now, different people cast this out in different ways. You could think of it. You could think of an ersatz possible world as a collection of propositions. Some people think of it as collections of states of affairs. You might think of it as a collection of facts. The Barnes and Williams model is kind of neutral with respect to that specific characterization. All they require is that it's not concrete, that it's abstract. The maximal side of things is the following. For every proposition P, with the every being universally quantified over an appropriately restricted domain, but for every proposition in the appropriately restricted domain, the world that you're assessing, the PPW, either opts for P or it opts for not P. Now, opts for is a bit vague, and the way you cast that out is going to depend on how you think about ersatz possible worlds. You know, if you think of it as sets of propositions, then the opting for will just be set inclusion or set membership. However it goes, the idea is a precisificationally possible world will give you a determinate answer to the question P. I don't know. I don't actually know how to format that as a question, but you know what I mean. It'll assess the truth or falsity of every claim of the form P or not P. It's classical in the sense that it doesn't violate the laws of bivalent logic. So in particular, there's no precisificationally possible world for which the truth values are associated with particular propositions are not either true or false. And so now we can characterize metaphysical indeterminacy in the actual world, or indeed any, say, nomologically or metaphysically possible world, by saying the actual world is metaphysically indeterminate if and only if it corresponds to more than one PPW, and corresponds with can be cashed out by the idea that no precisificationally possible world determinately misrepresents the actual world. So think about the semantic a semantic gloss on this, and go back to the idea of baldness, right? Supposing you've got the predicate is bald, and there's a person with, I don't know what I don't actually know how many hairs a non-bald person has, but let's assume that one of those borderline cases is having, say, 5,000 hairs. So it's not clear whether that counts as bald or not bald. So any precisificationally possible, in this case, model which says that corresponds, that corresponds to a person being bald, doesn't determinately misrepresent it, because that's one of the borderline cases. And similarly, any precisificationally possible world that says it doesn't correspond to baldness also doesn't determinately misrepresent it. And so the idea is, if there's this kind of fuzziness in the world, then any precisifications that are consistent with that fuzziness will correspond to the actual world. So if it turns out that the actual world is not metaphysically indeterminate, then there's only one precisificationally possible world. That's the basic idea. So that's all I'm going to say about how to model metaphysical indeterminacy. Let's talk about a sort of what you might think of as a semantic correlate, and that's this notion of definability. Now, definability has a very, very specific characterization depending on whether you're doing first order logic or higher order logics. There are notions of implicit and explicit definability, but really what all of these notions are trying to capture is something like an answer to the following question: what are the sorts of things that we can talk about in a given language? And of course, when we're doing, in the example over here, I'll just do simple first order semantics, but when we're doing semantics in general, what we want to do is we on a model theoretic approach, we define what are known as structures. I'm not going to use the word structure because I use the word structure in a different sense. So I'm going to use a term that I stole from Neil Dewar from his 2015 BJPS paper. Well, from his paper that's in the BJPS now that I read in 2015, where he uses the term picture in place of what a logician would call a structure. And all that consists of is a universe of discourse, a domain of discourse, and an interpretation function. That is, for any language, the interpretation function is going to take all of your predicate symbols, your n-place predicate symbols, and map them to n tuples in the domain. This is straightforward sort of first year model theory. Now, I'm not going to give you the actual definition of definability. What I'm going to give you is a consequence of that definition, which in some sense is more general than any specific definition. And that is a necessary condition for the definability of a particular relation, is that it's invariant under the automorphisms of the picture that I've just given you. A simple example is, imagine I've got some domain with, let's say 10 objects, 5 of which are very definitely green and 5 of which are not green. And I want my language, I want to ascribe to a predicate symbol in my language a sort of link to the property of greenness, such that that predicate means green, and the extension of that predicate is the property of greenness. Now, if it turns out that someone comes to me and says, "Here's the picture that you're allowed to work with. You're only allowed to work with this picture, and pictures related to this picture by automorphisms." And I say, okay, that's fine. I've got a one-place predicate, and that one-place predicate's extensions under this interpretation function take me to all and only the green objects. And you go, that's great. But now we worry about permutations of the domain that are automorphisms of this picture. And supposing there are allowed permutations on this domain that don't change the structure of this picture, such that I map a non-green object to a green object, what's going to happen is that with respect to that language, with respect to the picture associated with that language, I'm not going to be able to define greenness. So if my speaker is only restricted to that particular linguistic setup, then there's going to be a semantic indeterminacy associated with the concept of greenness. I'm not going to be able to say determinately whether the object that I pick out in the domain is green or not. So undefinability, I propose, can be thought of as a sufficient condition for a kind of semantic indeterminacy. Good. Now let's get back to talking about indeterminacy of location. So recall in the last section, I presented this idea of arbitrary localization in metric terms. And I said, look, the way that we're going to be able to talk about arbitrary localization is if we can define distances, arbitrarily small distances. So now we can talk about definability more specifically, and in particular, we can talk about the definability of this two-place relation of spatial separation. Now, on a manifold, I can define an arbitrarily small separation if that relation that I've called R mu is invariant under the automorphisms of the picture that I associate with the theory that I have, in particular with the theory expressed in these metric manifold terms. Now I can ask the question, can I do the same thing algebraically? Of course, the answer is yes, because I had an equivalent relation, which I've called R star. And this, for a commutative algebra, is perfectly fine, right? I can define, I've got a perfectly definable relation of arbitrary separation. But of course, the punchline is once the algebra ceases to be commutative, R mu is no longer definable for arbitrarily small mu's. And of course, the value of the mu is going to depend on the theory under consideration, but in general, there's going to be some kind of obstruction that's going to be characterized by this minimum distance. That's going to mean that I can't define arbitrarily small separations. So, according to the language that we sort of naturally associate with non-commutative geometries, it seems like arbitrary localization facts are going to be at least semantically indeterminate. And so now the question is, okay, they're semantically indeterminate. Does that mean that I've got an example of metaphysical indeterminacy? And this is where we're going to come to two conclusions, what I call the weak conclusion and the strong conclusion. The weak conclusion, I think, is yes, we've got an example. We can argue that this is an example of metaphysical indeterminacy. And I actually think there's a lot to be said for this. And there's also a lot to be said for the idea of thinking about spacetimes and locations in non-commutative geometries in terms of indeterminacy rather than in terms of discreteness. But I'll say more of that a little bit later. I imagine that a proponent of the weak conclusion, will want to accept a condition of this form. There is metaphysical indeterminacy out there in the world. The Barnes-William model is adequate to represent this metaphysical indeterminacy, and therefore, and as a consequence, non-commutative geometry is metaphysically indeterminate with respect to location. How can they make this claim? Well, the arbitrary separation relation is not definable in the actual world, in the actual NCG world, but it's definable in every precisificationally possible world. And indeed, in every precisificationally possible world in which this is definable, it is not the case that any of those worlds determinately misrepresent the actual non-commutative geometric world. So what we've got is a property that one could ascribe to particulars in the actual world, but the actual world is in some sense unsettled between different choices that it could make about that property, or in this case, about that relation. And I think this is one way to make sense of an objection that Eric threw at Nick and indeed at all of us in an email thread later, when Nick talked about the idea of operational significance of things like points. And I'm paraphrasing, but I think Eric's objection was something like this: geometrical structures, whether they're points or tangent spaces or vectors or whatever, they can be given physical salience in ways that are independent of just operationalizability or measurability, right? And if that's the case, if they are being given physical salience and in some sense physical meaning by things other than measurability, then I should be perfectly, I should be allowed to talk about points, even if it's the case that my measuring devices can't resolve below a certain level. Now, if that's true, and if that's a good argument, of course you then have to demonstrate that points are physically salient in some other way. But assuming you've done that, and assuming it's the case that non-commutative geometries are blind to those regions, then I think you can perfectly well make the argument that non-commutative geometries, or the NCG worlds, are metaphysically indeterminate. And I think, as I said, there's a sort of long history. We've kind of grown accustomed to the idea of points playing an important theoretical role. And so if we think, well, they play an important theoretical role, they are therefore intelligible, I think you can then say, yes, I can make sense of the notion, or at least I can make sense of the meaning of the word point, but now in a non-commutative geometry, it's metaphysically indeterminate what the location of a particular body is. I want to resist that slightly. I think that's slightly too weak a conclusion. My stronger conclusion focuses on something that we've kind of glided past, which is this question of where these precisificationally possible worlds came from, right? Remember, I characterized a precisificationally possible world as a maximal and classical ersatz world. But we should be careful not to think of maximality as corresponding to classical mechanical precision, right? in classical mechanics, we could perfectly well, at least in theory, arbitrarily localize things. And so we've got this intuitive idea that it should be precisificationally possible by the standards of the language that we use to talk about classical theories to talk about arbitrary locations. And I think this is just a holdover from a particular view of classical mechanics. And I think a sort of a broadly empiricist impulse will mandate something something a bit stronger than that. It'll mandate the idea that points get their physical meaning only via the kinds of things that points are in a position to explain in a way that nothing else can explain, right? If it's part of an ineliminable description or explanation of some phenomenon, then I think points are in good standing. But as I've hopefully made at least plausible, we can recover sort of empirical descriptions, or at least if we can recover empirical descriptions without points, well, then so much the worse for points. And so then if the project, then we sort of have a very well delineated project, right? The question is, how do we then recover the apparently spatiotemporal world from a description that we can give, which completely eschews the notion of a point? I'm not going to say anything about that because that's precisely what Nick talked about last time with his CDP proposal. I think that's, I don't have an answer to this question. I think Fidelia is a very good person to ask about sort of cutting edge research in this direction. So let me finish by just giving you a positive proposal and a sort of positive lesson to be derived for metaphysics. I suddenly realized that it's incredibly dark. Sorry, let me just switch on the light. Ah, so much better. Sorry. So my proposal is, let's think a little bit more carefully about how we populate the space of precisificationally possible worlds, right? Let the vocabulary be determined by the algebra. I've said observables here, which I haven't said before, but in general, the algebras that we've been talking about, and possibly other components of the physics. If we incorporate other components of the physics, we'd have to give some justification for their inclusion. But once we do that, we're going to realize that physical properties, or at least one can argue that physical properties and indeed relations that we talk about should be all and only those that are invariant under the automorphisms of the picture that's determined by the physics itself. What's going to happen then is each of these proposals is going to have to justify its inclusion. So if you're someone like Laura Rucci who wants to justify the inclusion of things like parochial observables in addition to just the straightforward algebra of observables, I think the kinds of arguments that she gives are really compelling and really convincing. And so we say, okay, let the vocabulary be determined by the algebra of observables and the parochial observables, and whatever else you think has a good claim to be in our vocabulary. The claim that I want to make is that points do not satisfy this criterion. So what's going to happen is a number of sort of things that were classically unproblematic will now no longer be part of our description. And I think that's good, because I think what we need to do is we need to judge determinacy by appropriate standards. I mean, we don't call Newtonian mechanics indeterminate just because there's no center of the universe. We don't call Newtonian mechanics indeterminate by the standards of Aristotelian teleological cosmology. So why should we call things like quantum mechanics or noncommutative geometries indeterminate by the standards that may not be appropriate to that particular physical theory? That's pretty much all I wanted to say. So that brings me to the end of the talk. Let me briefly summarize and then take a couple of minutes. I assume there's going to be a short break before the Q&A, and then sort of launch into the Q&A. So broadly speaking, sorry, there was a lot to get through there. Broadly speaking, at least my interest in noncommutative geometries can be thought of as being motivated by impulses to talk about things like generalizations and unifications. And the project was to find a formalism that was extensionally equivalent to differential geometry, so that we could think of differential geometry as just a kind of special case of this sort of broader formalism. And then what happens is, when we find this broader formalism, which I contend is this algebra first formalism, it unearths important metaphysical presuppositions. For example, that space-time, you might have presupposed that space-time had to be a continuous manifold and not something discrete or metaphysically indeterminate. And so it might turn out that some presuppositions are justified, might turn out that others are not. But the important thing is to do the hard work in establishing that they are in fact justified. And I think what I hope that we've shown in the paper, and I hope that I've gestured towards today in the talk, is we can talk about space-time without it being indiscrete. Simon didn't say anything about me not being allowed puns during the talk, so I thought I'd just slip that one in there. So the final slide, the take-home messages, right? I think I would like to think that I've argued that the claim that there are no arbitrarily small areas is on fairly good philosophical grounds on the basis of how we should think about metaphysical indeterminacy. And that leads to thinking of the first claim as a sort of disjunctive claim, right? Either you can think of locations as being metaphysically indeterminate, or you should just say, no, we should just throw out talk of arbitrary locations in the first place. That's just a sort of holdover from physics that we shouldn't take seriously, at least at the fundamental level anymore. That's me done. Thank you.
Hi, Tushar. Great question.
Hi, Enrique.
Great talk. Really nice. Very well.
Great question. I can say in advance already, Enrique.
I'm sorry. So the first question actually is if you rehearsed to get the right book when you turned around beforehand, but that's not really my question. Yeah.
So it depends on what you mean by rehearse. I've done this so often that it is muscle memory at this point. So yeah, but no, it wasn't rehearsed specifically for this talk.
Okay. So I have a question about metaphysical indeterminacy, and I hadn't come across it before. And I'm used to the Lewisian version, where it's just semantic indecision, or vagueness is semantic indecision. And and clearly this is an indecision that remains after everything has been processified as much as possible. So it's not encompassed by the Lewisian version, it seems, although, that version seemed to me to be independent of the physics. And so,
yeah.
And so I wanted to know a little bit about that, and maybe the way that I'm understanding the indeterminacy is a little bit like in gauge theory, to have some property of a gauge potential that you can look at every representative, but is gauge variant, so it doesn't represent anything physical. And so it's not, would that be, so it's not defined in that way. And so I'm trying to link that up to the Lewisian world.
Yeah, okay, so I was right, that was a really good question. I think the gauge thing is not really what, at least what the proponents of, I'm just going to say MI because I can't keep saying metaphysical indeterminacy, what proponents of MI in the literature have in mind. The standard sorts of examples that you see, sort of independently, well, I was about to say independently of the physics and then immediately say quantum mechanics. The sorts of things that they have in mind is not so much there are certain properties. Okay, let me put it this way. There's a constant debate about the sort of physical significance of things like gauge potentials, but by and large, the idea is they in some sense correspond to descriptive fluff, right? To sort of representational excess or whatever. And so it's really just it's a fault of our language that we've got this extra bit of structure. The proponents of metaphysical indeterminacy don't want to say that. They want to say something like our language is sort of precise enough to allow us to get a grip on the kinds of properties that might be instantiated in the world, but the world just isn't kind enough, or isn't sort of is in some sense what's the word I'm looking for? My mind's gone blank. Is it deficient? That was the word I was looking for. The world is in some sense deficient, and so it's not the case that so it's the case that there's some like sort of bona fide genuine property that something might have, and some bona fide alternative sort of realizer of that property that same thing might have, and yet that thing doesn't make a decision as to whether or not it has it instantiates one of those properties rather than the other. There are various examples in the literature. One set of which comes from quantum mechanics. So some people have argued that as a result of the Cauchy-Specker theorem, for example, there's going to be metaphysical indeterminacy because take your favorite like Merman spin pair setup. You can't ascribe the same spin property to sort of all of the particulars at the same time. And the idea there is there's an obstruction in a kind of global ascription of properties. That means that even though each of these individual properties is sort of perfectly intelligible and well described and whatever, there's just some weird fact about the actual world that precludes a straightforward description. And so in that sense, the gauge example is not, I don't think, the kind of thing that would qualify.
Great, Leah.
Great. Hi, Tushar. A very lovely talk. Thank you so much.
Thank you.
That was really, really interesting. So I just had a clarificatory question about kind of what we're losing, I guess, from the traditional description. So you mentioned points, but so I'm kind of wondering if we lose points, I guess if we lose kind of a determinate description of metric structure. So kind of what's the scope of things that we're losing if we're considering this kind of alternative framework?
Good, yeah. So you're right. I just focused on points because in a sense that's sort of the a kind of nice way to sell it. But you're totally right. You lose not just points, as you say. So take metric structure, for example. What you lose is, so what you have is an idea, is a way of talking about distances sort of larger than a particular lower bound. But what I didn't say was, when you talk about distances larger than that particular lower bound, you're never actually going to be precise about those distances as well to within the that new factor, right? So what's going to happen is what you're going to lose out on is not just this idea of arbitrary localizability, but also this idea of arbitrary precision of length measurements. And the way around it is just to say something like, look, we're used to this kind of thing from ordinary quantum mechanics as well, right? We're used to kind of classical for all practical purposes, and we're going to have to do something along those lines as well. And then ultimately it just comes down to, well, look at the kinds of experimental outcomes that we have. Are any of them resolved to metric scales, to sort of metric precision below such and such a scale? And if the answer is no, then it's just then the response is, well, I've reproduced all of the physics that you wanted to, and I've done away with not just locations but also arbitrarily precise distance measurements. Excellent, I've learned something about the world. So yeah, I think that's a really good question. I think, this is, as you said, this is just off what you said, but there are plenty of other things that I imagine that you'd miss out on, sort of arbitrarily precise angles, for example, things like that. So yeah.
Just any kind of arbitrarily precise geometric structure. Geometric measurements.
Yeah. Again, I'd be a little bit careful about how we characterize arbitrarily precise, right? Because one of the things that I wanted to say is like this stipulation that something is precise is always going to be against a sort of backdrop of assumptions of linguistic assumptions, right? But yeah, against what you might think of as just a sort of unproblematic background of sort of the assumption of continuous manifold, then yeah, those are the things that you'd lose.
Okay, thanks.
Oliver? Oliver, I think, sorry.
I thought you said Lola.
No.
So thanks very much, Tushar. I want to ask about the metaphysics again, and I'm still struggling to know how the picture's meant to work. And it occurred to me that there are actually two different ways you could go. So one says, take the case of the commutative algebra. The right way to understand the ontology, roughly speaking, is in terms of a differentiable manifold, kind of four-dimensional worlds, spatiotemporal things with their various arrangements. And here's how to see this algebraic formalism mapping onto that, and how to describe the stuff that's more perspicuously described in differentiable manifold terms as related to the algebraic stuff. And then when you go non-commutative at the algebraic level, the story should stay roughly the same. The way to think about reality is as the kind of analog of the differentiable manifold was to the commutative case. So that I can sort of understand, and it's a kind of, there's this gap to be further articulated. And then you point out, well, certain things that were defined at the differentiable manifold level when you had a commutative algebraic structure are longer defined, and you kind of can adopt a sort of quietistic picture. So to the extent that I can talk about these things, that they're living at, the differentiable manifold level, but of course there isn't such a thing. A different way of thinking about it is, no, somehow the algebraic language is just more metaphysically perspicuous. That's the language we should adopt to describe reality. And faced with that suggestion, I've no idea what's going on. So am I right that the first proposal is closer to what you're sort of exploring and advocating?
Yeah. Right. Thanks a lot, Ollie. That's really helpful. That sets it up really nicely. I mean, I tried to be, obviously wasn't sufficiently careful about this, but tried to be careful when I use the word fundamental. I should probably just never use the word fundamental, but the way you set it up is perfect, because what I want to say is, you use the algebra as your sort of your first point of contact when it comes to sort of trying to derive metaphysical lessons, and in doing that, what you want to end up doing is, and I didn't stress this enough in the paper, but I think you're exactly right. We want to be able to recover something that sort of looks like, that looks not very different from the sort of higher level picture that we have with the commutative manifold. But having done away with the idea that, just because we can talk about locations at the higher level, we can talk about arbitrarily small locations. Arbitrarily, whatever, precise locations. But nonetheless, the sort of the picture that you want to describe is one on which you still basically have sort of stuff in something, right? You've got objects in some place. I think the way that you set it up is precisely how I want to say it. The algebra is just going to be a guide to tell you what parts of that picture that you might think of as being unproblematic is something that you should get rid of. But the overall picture, the overall sort of intuitive, the overall idea that I should think about the metaphysics as one on which I've just got objects in something, I think that is not affected. So I'm not trying to. So I don't want to argue. I mean, we canvass a few options in the paper. This is stuff that Nick wrote about a lot. We canvass the ideas that the idea that you can take the algebra as metaphysically primitive. I mean, this is stuff that Nick also mentioned in the Q&A session last week. But my personal view is, until I'm sort of pushed into the corner and sort of forced to accept that that's the only way to do things, I think the way that you've set it up is really what I'd want to argue. Just use the algebra as a guide, but sort of only give up the metaphysical intuitions that you're forced to give up in this sort of intuitive picture.
Great, thanks.
Nick had the finger.
Okay, so I sort of have the opposite answer to Tushar in this one, I think. I mean, I think if I understand, maybe we're not hearing your question in quite the same way, but I think what I was arguing for was to take the algebra pretty seriously as at least playing around with the idea of taking the algebra seriously as the sort of fundamental ontology. And then, the picture I had in mind, very crudely is, just sort of old-fashioned, kind of empirical meaning picture. So this is how I would sort of address your question. So yeah, the world is fundamentally algebraic. That's the sort of upshot of this. How do we understand that? Well, clearly we can understand it internally by, we understand the formal structure of this algebra. But as with any sort of theoretical entities, right, the troublesome terms, we have to kind of give some empirical meaning to those. And that's done by cashing out what the algebra says experimentally, or empirically, which is kind of what the CDP sort of ansatz and is supposed to be doing for you, if you want to think in those terms. It's kind of telling you how those sort of purely formal algebraic relations, through the theory, hook up to the world of experience and experiment, sort of fairly standard kind of philosophy of sciencey kind of way. So, and sort of the argument there would be, we've kind of shown there, we have field theory, but they're not, the unit of physical significance is not, there are no points, so it can't be the point values of the fields, it's the whole field, which is just representing an element of the algebra. So I like the way you set it up, but I'm going for the second option. It sounds like Tushar's going for your first option.
I mean, I don't know how far apart those two options really are, but I know there's a queue, so I'm happy to talk about this at the end when if anyone wants to stick around.
And Fidelis keeping quiet on this question.
All right, fine. Let's go to Adam, unless you want to carry on working it out. But let's go.
Sorry, who was the you directed at?
No, well, I mean, so there's a discussion between the co-authors, and you can carry that. You can go to Adam and have that discussion at the end.
I'm happy to go to Adam.
Okay, thank you so much for your talk, Tushar. If I wasn't about to ask a question, I would have had a finger just to say that I'm unclear that Nick's suggestion is giving a metaphysics rather than not giving one. But anyway, the question was about these PPWs. So I apologize if you even said it and I missed it, but I'm just wondering what the scope is. Given an NCG picture, what's the restriction on possible PPWs? Is it? Do I just think of it by analogy with a negation incomplete theory and all of its possible completions? So it's just all the ways of throwing sentences not already in the set, such as to preserve its consistency. And I just wondered whether there might be any mileage in putting extra restrictions on a PPW. And I was thinking an analogy with the Koch-Specker theorem. You might say, well, I don't just want to be able to throw any old sentence into this negation incomplete set. I want to preserve certain functional relationships and so on. And I just wondered if there's any mileage in worrying about that.
Yeah, I mean, I think that this points to a sort of a deeper question just about the setup of the PPWs, right? Because it's supposed to be maximal, and so that's quantifying over a particular kind of over a particular domain of propositions. And the question is, well, how do we characterize that domain of propositions? It can't just be all propositions. I don't even know what that set looks like. And so what I want to suggest is something like, I mean, it's a bit hand. This is not hyper precise. But what I want to suggest is something like, assuming that I know what it is for a proposition to be about something, right? Big assumption there. But assuming I know what that is, I want to restrict the propositions available for my PPWs to be the propositions that are about the world as described by the physics. And what I mean by that is propositions and and sort of various kinds of manipulations on those propositions that are built out of that are basically built out of predicates that are definable in a language that I with respect to a structure or picture that I assert is the correct picture for that particular physical theory. And so now this sort of shifts the burden onto, well, how do I determine what the appropriate vocabulary and what the appropriate picture is for a physical theory? And that's when that's where the sort of positive proposal, which is start with this algebra, certainly all the predicates that correspond to things that are invariant under the automorphisms of that algebra, that goes in with no problem. And then it becomes sort of just the standard kind of game that you have to play when talking about sort of language that's appropriate to, or choice of vocabulary that's appropriate to a physical theory. And so I gave the example of Laura's parochial observables. There might be sort of other things in there. I don't have anything much more specific than that, but I'm hoping that that's sort of sufficiently gets across the idea of how I want to set up this language. And then once I have the language, basically what I want to argue is once I have the language, I give into some kind of naturalistic impulse that says, look, I should only be allowed, I should only be allowed to make claims that are sort of scientifically kosher. Then what that's going to do is it's going to rule out a bunch of sort of what you might think of as sort of odd metaphysical claims, just on sort of straightforward semantic grounds. I should just add that I've been working on a paper where I argue this in the context of quotient spectra, sort of precisely along these grounds. So I think that's a good testing ground for these sorts of claims, possibly even a better testing ground than NCGs. Sorry, that ended up being a bit longer than I'd intended. Sorry.
No, thank you very much.
Jeremy?
Thanks, Alex. Thank you, Tushar, for a wonderful talk. Can I ask you my most broad philosophy question, and then I hope we can talk privately about other things. The broad philosophy question is, I'm anxious about metaphysical indeterminacy. I haven't read Barnes and Williams, I confess, but you can imagine it's the obvious worry. Once I've eliminated all semantic indecision and I've got all knowledge, and then I'm told there is a residual variety of the ways things could be, so to speak, or there is indeterminacy that remains. Call it not variety of the way things could be, because that sounds like the first step towards further precisifications spread out in a range of smorgasbord of precise options, right? But it is fancy footwork, isn't it, for the human mind to have a coherent picture of something remaining open or various or alternatives after you both know everything and have decided with complete precision what to mean by your words. So anyway, I'm worried. But here's my specific question, which may help. In your green example, you said undefinability implies semantic indeterminacy. Right, okay. That's a bit contentious, because somebody might say, not all my words need to be definable in terms of the picture in order to have a definite and crisp reference or extension. So I claim that being undefinable simply means the extension isn't fixed by the automorphisms of the picture. And following on from that, I just didn't quite get how, when we had the first display of weak conclusion, how are we going to actually get from the undefinability of R mu star to something beyond semantic indeterminacy? How were we going to milk that to make a claim that NCG is giving us this MI, which I do, for the first stated reason, find a dizzy idea anyway?
Thanks, Jeremy. I mean, the immediate answer is I think you're completely right, and I think that's why that's sort of why I want to opt for the strong option. So there were two things in there. So let me address the first thing about this idea of residual indeterminacy, sort of skepticism about this idea of residual indeterminacy. I completely agree that that this is going to be a problem, unless there's some claim that you can make that there's some language with respect to which I'm making descriptions about the world, and then there's this other sort of more precise, deeper metaphysical language that I've sort of been born with or been blessed with by an oracle. And it's true, you can only make claims that you can give it the name metaphysical indeterminacy, but really it's an indeterminacy of this language by the standards of this metaphysically privileged language. And so I think the skepticism that there's something sort of there's some kind of metaphysical indeterminacy beyond any semantic indeterminacy, I think that's completely wrong. Because in order to just set the thing up, I think the way to think about it, at least the way I think about it, is what metaphysical indeterminacy is expressed in terms of some kind of metaphysically privileged, incredibly precise language. but ultimately this whole game that we're playing is still entirely semantic. So I agree. I agree that that one ought to be skeptical.
Now I understand the meaning of your second main message about appropriate standards. Okay, thank you.
Yes.
Okay.
I've forgotten what the second. I've forgotten what the second.
No, well, never mind. Thank you. I should let other people go. That explains why NCGs were being ruled MI, because they're MI in this relatively Jeremy comprehensible sense, that they go beyond what the metaphysically less than just perfect, totally discriminating language can distinguish. Yeah, thanks. Yeah.
I have a tiny finger on this, I think, if I'm allowed. So I was wondering whether or not sort of all emergent properties would lead to metaphysical indeterminacy. And for example, say if you've got like an entity being liquid or an entity being green or red or whatever, and then you say that those properties don't apply to particles, does that lead to metaphysical indeterminacy? And then the answer that it just depends what your kind of privileged language is to describe these things.
Yeah, thanks for that, Alex. I think that's a really good question. I think at least the way that metaphysical indeterminacy is generally presented is it's presented with respect to the final fundamental ontology or whatever. I think you would be wrong to say that emergent properties are metaphysically indeterminate, because I think the property of being metaphysically, the property of something like a fact or whatever being metaphysically indeterminate is only appropriate to a certain subset of sort of all of the facts that we could have. In particular, I think it's only right to refer to that. It's only right to characterize facts about the fundamental ontology as facts with respect to which you can be metaphysically indeterminate. Now, that isn't to say I'm using fundamental in the metaphysical sense. I'm using fundamental in the sort of primitive with respect to your domain of discourse sense. So color could be metaphysically indeterminate with respect to some domain of discourse in which you've got objects that are larger than particular wavelengths so that you can correctly ascribe color. Sure, I can think, it's an emergent property, but it's metaphysically indeterminate with respect to the appropriate domain. With respect to the domain of, atoms and electrons and whatever, things that can't have colors, it's something like a category error. It's not, I don't think it's right to say that it's metaphysically indeterminate. It's just, those are not the sorts of properties that can be instantiated by those particulars. So those these claims are always up against a sort of background set of presuppositions. And I think what I want to do is sort of make explicit the sort of presuppositions about the domain in this case.
Great, thank you. That helps a lot. Neil?
Yeah, thanks, Tushar. That was cool. So I think, I had a relatively flat-footed question that I think has now kind of, the answers which have sort of emerged in your discussions with Adam and Jeremy, which was just, what was the sense in which we were able to say there is this relation which is undefinable? And I think it sounds like it's, there's sort of two languages in play. There's this more restricted algebraic language, and there's this richer language. The richer language is able to describe this relation of being within mu distance of one another, but presumably models of that richer language don't correspond one-to-one to, there'll be several models of the richer language that will correspond to a single algebraic model, and it's that in that sense.
Yes.
Good. Okay. Can I also ask then a little bit about the sense in which we should think of this as a relation of indeterminacy rather than I don't know, this is it that picture of there's sort of these multiple enrichings of the algebraic, so there's these multiple, I guess, representations of the algebraic the same algebraic facts in geometric terms, that's, and so we're to think of the indeterminacy as being because the algebraic facts, which we're taking to be the true physical facts, don't pick out a unique kind of geometric story.
I think that's one. I think that's a good way to think about it. I haven't thought about it in that way, but I think that's one way to think about it. And I think, I mean, it'll help. You were at Nick's talk a couple of weeks ago.
I wasn't, I'm afraid.
Anyway, okay, fine. So
sorry, Nick.
Sorry to sell you out there, Neil. So anyway, okay, so let me not use that example. I think so here's I think this is slightly related to the way that I've been thinking about it in the last 10 minutes since Ollie's question. What is the metaphysical story that you want to tell? Well, it's the one that's in a sense going to do the least violence to sort of the stuff that's worked for our metaphysical pictures of the world according to science in the past, right? And all we do is sort of substitute for Newtonian mechanics or GR, non-commutative geometry, and see how much we can still hold on to. Now, what the representations of the algebra are doing, compare a non-commutative geometric representation of some algebra observables with like an algebraic characterization of a Newtonian system or some classical system, right? That algebraic description is going to have one representation in terms of a manifold. In fact, it's going to have plenty because it'll be up to diffeomorphism, but basically up to diffeomorphism have one representation on the in terms of manifold. And we have some reason to kind of metaphysically privilege that representation, not in the sense of saying that the other representations don't contain all of the important moving parts, but instead to say that's the representation with respect to which I can be clear about what I mean by things like locations and objects being moving this in such a
sorry, the other representations of a commuting algebra.
Of a commuting algebra.
Yeah.
Right, because I can represent a commuting algebra on like an uncountable set of T-blocks, right? So so the reason that I'm going to represent it on this particular on what I think of as a space-time manifold is because I have this idea that I can then do metaphysics, and then if it turns out that sort of very symmetry considerations mean that I need to throw out primitive transworld identity of points, so be it. But that's going to sort of, that representation is going to be in some sense privileged, but sort of cognitively privileged. But that's it. What's going on in the non-commutative case is you can actually represent this algebra on a manifold that is itself commutative. It's known as the Weil representation. So I guess I did talk about what I wasn't going to talk about. But now the algebra functions is defined with respect to this weird star product. It's no longer just the pointwise inherited product from the real numbers. And so now in this case, what I'm saying is it's in a sense,
but it's still an algebra of scalar fields, but just with this
weird
product,
with this kooky product, right? And so now what I'm saying is this algebra, sort of thinking about things in this way, it might still in some sense be cognitively sort of preferable because I feel like I can make sense of properties ascribed to points on a commuting manifold, but that just have some weird kind of global behavior that's encapsulated, like by global I mean non-local behavior that's encapsulated in this weird star product. But what's happening in that case is the weird star product is making me really acutely aware of the sort of representational in idiosyncrasies. And so what I want to say is, look, this is just one representation. It's sort of cognitively privileged. But as long as I'm aware of the things that are representation independent, that I can nonetheless talk about with respect to this representation, I'm fine. So I guess that was sort of a long-winded way of saying we basically just need to be careful about what sort of things are artifacts of our representation and what aren't. And I think the non-commutative geometry, the non-commutative algebra, is a way of at least putting up for debate certain properties, even in sort of commutative theories, that might be such that you could think of them as sort of artifacts of the representation.
Right. Good. And just, sorry, one final very quick technical question. So this latter kind of representation, so representation in terms of star products, that will not in general be unique up to diffeomorphism in the way that, or is that unique up to diffeomorphism in the way the commutative?
Oh no, is the question? No, it's not going to uniquely, it's not going to be expressible as uniquely as,
Okay, great, thank you. That was very helpful.
Adele, is your comment on this, or should I add you to the end of the queue?
It's a bit No, I think I better do it now because it was inspired by the discussion. It's some sort of a general issue, however. I think that there are two levels in which the discussion should be done. One is a purely mathematical level, in which the non-commutative geometry in mathematics started with Gelfand, Naimark, and other people, but it's an algebraization of geometry so that you can generalize it to non-commutative algebras. So this is a mathematical aspect, and of course, all the discussions that you made can be applied at this level. But then there is another level, which is the applications to physics. Now, physics is sometimes said that it's mathematics with scales, but there is another important element there. And the fact that we are hoping to apply this to quantum space-time and field theory and these other things, then we should recognize somewhere space-time, which cannot be just a limit, because like in quantum mechanics, making a limit is not such a well-defined thing. So this is an important aspect. The paper is not discussed, but the aspect of deformation. So we have a physical theory, which is based on points. And then we need these points to define our physical theory, but we have to deny them because they don't exist, because they cannot be there. This is the assumption that a quantizing space-time will make this. So now this is something which there is tension. There is already this tension for quantum mechanics, but there is position and momentum. They are two different objects, and therefore one can stay with the fact that we can define position but not momentum. But now in space-time, you cannot define the points which make up your space-time. So this is something I purposely refrain from using any of the jargon of philosophy because I just don't know it. But there is a point, there is an important point of non-commutative geometry, and also the demarcation line between mathematicians and physicists. If we do non-commutative geometry for physics, you should find somewhere space-time, because it has served us very well for a few centuries, and we cannot throw it away, of course. So this was just my comment, which applies to several things. Okay, thank you. Sorry.
Thanks. Tushar, do you have anything you want to say to that, or are you?
No.
Okay. Jacob is next.
Thanks so much. Wonderful talk, Tushar. I really enjoyed it. First, just an apology. I needed to step away briefly during the question session, so I may have missed some answers that may pertain to my questions. If I have, just please feel free to punt. So I have two questions. One is a quick technical question on the motivation part of the talk, and the other is a little more conceptual. So first, a quick technical question. I was under the impression that classical non-abelian Yang-Mills theories could arise from Kaluza-Klein compactifications without a need for non-commutative geometry, just from the shape of the compactified extra dimensions. Like the Lie group of the Yang-Mills theory corresponds to the isometry group of the extra dimensional manifold. But I think in the beginning of your talk in the physical motivation, you suggested otherwise. Am I incorrect here? Am I missing something?
No, I mean, I did suggest otherwise, but again, I guess I'm going to play my, this was sort of fuzzy and vague, intended to just sort of pump intuitions about this card. Yeah, what I sort of, thinking about things thinking about the non-abelianness, thinking about the non-abelianness of the gauge group giving rise to commutativity. I think of the non-abelianness as sufficient but not necessary. So it was just intended to motivate that.
All right, I figured that's what it was, but yeah, I just wanted to clarify. That's why it was just a quick technical question. The second might be related to, so I was here when Jeremy asked this question. So my second question might be related to his question. Mm-hmm. So Tushar, your definition of metaphysical indeterminacy was a negative one, right? That it's any indeterminacy that remains residual after semantic and epistemic indeterminacy has been ruled out. That's all I mean by negative.
Yeah.
So presumably, like ontic, if there's some notion of ontic indeterminacy, that might fall into that category, metaphysical indeterminacy. I'm just wondering what else might fall into that category. So when you spoke very quickly about epistemic indeterminacy, but you know, epistemic indeterminacy, at least the way I think about it, it can have subjective aspects, just two different people who show up at an experiment for which there is a well-defined result may just have different knowledge about it. They may assign different subjective Bayesian probabilities for it. But you know, on some interpretations of quantum theory, there can be objective aspects, right? Objective epistemic aspects. There can be objective probabilities. Are you imagining that both kinds of epistemic indeterminacy lie on the same side of your metaphysical indeterminacy side, or would you allow that subjective epistemic indeterminacy could lie on the non-metaphysical side, and objective epistemic indeterminacy, should it exist, lie on the metaphysical side, along with maybe ontic, presumably ontic indeterminacy?
That's fantastic. That's really interesting. I hadn't thought about it at all. I'm assuming you're thinking of some kind of some kind of account of knowledge on which, you know, I know that P, if my credence in P, or you know, if the epistemic probability of P is greater than 0.95 but not necessarily 1, right? Yeah. In which case, at least on this way of thinking about things, I think it's that kind of thing would certainly come closer to what people have in mind about metaphysical indeterminacy, because I think, at least in the discussions that I'm aware of epistemic indeterminacy, I know that P is generally not cashed out in probabilistic terms. It's always sort of, you know, whatever the flavor of the month is, but it's always, you know, there's yeah. So given that, I think, yeah, you're right. What I should, you know, a tightening up of that sort of negative prescription for how to identify metaphysical indeterminacy would, well, the simple, stupid way to do it would be it's what remains after all the semantic and what everyone, or what most people in the literature have referred to as epistemic indeterminacy, has been removed. But I think the more positive statement of what's going on there, I think ultimately will probably be given in terms of the Barnes-Williams, or whatever model you're using for metaphysical indeterminacy. And I think and that's the way I sort of want to think about it. So the negative characterization I just want to think of as just that, a sort of intuitive characterization. And then I want the positive characterization to be, look, we know what, you know, assuming we've tightened up what precisificationally possible worlds are, and linguistic ersatz and whatever, that's going to be the positive characterization of metaphysical indeterminacy. And I think on that view, what you suggest as this kind of objective epistemic indeterminacy will count as a kind of metaphysical indeterminacy. That's what I would think.
Great. Yeah, that totally resolves what I was. Yeah, thank you.
Thanks a lot, Jacob.
So I noticed a few people are going, but I'm happy to go on for another 10 minutes. Are you Tushar?
Oh, absolutely. I mean, now the cricket match is over, I'm not missing anything.
In which case, there's time for Adam's question.
Thank you. I'm sorry, Tushar, it's not directly related to the main meat of your talk, but it was just something you said right at the end that.
Oh dear.
That's got me thinking.
Those throwaway comments.
You said it's just this idea that the physical properties should be invariant under all automorphisms. Mm-hmm. And I think I see the motivation for that, because invariance under all automorphisms is at least a necessary condition for definability, as you say, and definability is just supervenience, really. It's just what logicians call supervenience. Yeah. So really the idea is that a physical property is one that's that supervenes on the basic properties. So it's actually a familiar metaphysical story. But then I was thinking about a particular example. So in Max Black's two-sphere world, is the mass of one of the spheres a physical property or not? Surely yes. Yeah. Is it invariant under all automorphisms? Well, in one sense yes, in another sense no. I mean, of course, the value of as it were mass of Castor is invariant under a permutation of Castor with Pollux, because they have the same mass. But it's also I'm also mentioning Castor.
Yes.
So does that make it unphysical? It's just that ambiguity that I just can't quite work out how to resolve.
Yeah, I think, I mean, that's, so this is, this sort of reminds me of, there's a paper on the conventionality of simultaneity by Rob Reinasevich, where he sort of argues against the Sarkar-Stachel claim. He argues against the Sarkar-Stachel argument against Malamud by saying that their example violates this criterion of definability. And so you should because they say, according to the Sarkar-Stachel model, I think it's sort of functionally very similar to this black sphere thing, right? They claim you can talk about the upper cone as opposed to the lower cone, and then they use that to define a set of simultaneity relations, conventional simultaneity relations. And what Reinasevich argues is you can't do that because a single lobe is not definable. And I think I'm sort of taking a cue from that view of what it is to be able to define physical structure, or at least structure that's sort of that's kind of structure in our physical theory. I'm using structure very loosely here, but things in our physical theory that we can talk about kind of unambiguously. I do share the worry, because this is not something that Reinasevich argues for, but I do share the worry that that's too restrictive as a sort of necessary component for all physical properties. Because maybe I do want to say, sort of metaphysically speaking, there is sense to be made of the top light cone and the bottom light cone as sort of distinct entities, but my language is just not going to capture that.
My understanding of that debate was that Malamud has a symmetric causal connectability relation, and all one has to do is go to a temporally directed causal connectability. So it goes, it's the after relation, as Rob would have it. It's not. Are you saying that the forward lobe is not definable under that more restrictive notion of causal connectability? I think it would be, wouldn't it?
No, it's not going to be the forward lobe. It'll be the lobe that's different from the other lobe. But it won't specifically be the forward lobe, or indeed the backward lobe.
Well, anyway.
As I understand it, this is the bit that's not being recorded, right?
No,
this is the bit that'll be edited out, right? Oh God, what's worse than having a bit recorded that you don't want recorded? Well, having the recording of you saying there's a bit that's been recorded that you don't want recorded.
This is being recorded, but I could try and edit. But anyway, let's go.
I'm determinately shutting up now. Forever.
Sorry, no, that's really. I mean, the answer is that I don't have an immediate response to that. It's something that I actually have thought about, but I don't have a resolution to. So I don't want to sound stupider than I already do.
Chris is the last one.
Thanks, Tushar. I wanted to come back to the Cauchy-Specker case and then go back via that to the non-commutative parallel.
Mm-hmm.
So I've often thought that appeal to the Cauchy-Specker theorem does rather less in these metaphysical indeterminacy arguments than one might suppose, largely because the worlds which you might seek to be the precise worlds, the more precise, the worlds made precise, which are then going to be indeterminate with respect to needn't themselves obey the property structures which are required to derive the contradiction in the Cauchy-Specker case.
Yeah.
So, and as always, we should think of concrete examples like the de Broglie-Bohm theory. So, what's the parallel, the kind of parallel of the de Broglie-Bohm theory for the non-commutative geometry kind of case? So this is some way that the world is or could be where everything's kind of filled in the way that you'd expect it to be, but there's something else funny is going on, like equivalent to non-locality perhaps. So something that we might not like, but it's a matter of a choice. This is probably a difficult question. What's the parallel of that kind of case for you? NCG?
So this might just be wrong, but I would think sort of in many significant ways the equivalent of that is the Weil representation that I mentioned in response to Neil. So I mean again, so with de Broglie-Bohm you've got you've got a hidden variable theory that's nonetheless contextual, right? It's sort of everything's sort of kind of gerrymandering itself up at the wave function level to make consistent the claim that there's still this little particle sort of that's localized in such a way and has these properties, right? I think the analog of that is take your non-commutative algebra and think of that as think of each element of that algebra as a function on some manifold. But now those functions don't compose in the sort of pointwise R in a way that's derived from pointwise R4, and that brings in a complete a sort of radical non-locality, because then you just have to worry about absolutely every other point on that manifold. But then you can still say, and I think this is the kind of thing that, for example, Eric wanted to. I feel like I might just be putting words in his mouth, but this seems like the kind of thing that Eric wanted to say, which is fine. I won't go so far as to say, an oracle told me that there are points and therefore I should. I should go for the Weil representation. But if I've got stuff other than this sort of operationalization procedure for kind of imbuing my terms with meaning, and I can kind of make sense of, if not points, then sort of separation smaller than what I call mu, then surely that's the sort of coherent metaphysical picture. And I think the answer there is yes. And I think what you're going to be committed to there is the idea that your other sort of metaphysical, if I was feeling sort of impolite, I'd say prejudices. If I were feeling polite, I'd say presuppositions, are sort of mandating that you kind of sort of tread that very, very, very fine boundary. And I think the answer is yes, you can do that. So you can argue that on my view of semantics and my view of metaphysics, and spelled out in such and such a way, what this non-commutative geometry is really telling me is that there's still a world with a manifold of points, but my fields behave in this really, really weird, in a way that's governed by this weird star product, in such a way that there are sort of influences coming off from plus and minus infinity and whatever. So yeah, I think that's and I think that's something that you can say, but you really shouldn't.
So you think it's, as it were, worse in this case than de Broglie-Bohm is for the quantum case?
Yeah, I mean, in the sense that it's I guess I might be wrong about this, but my intuition is that you can still get away with certain properties being sort of at least quasi-local when talking about de Broglie-Bohm, and it seems like basically every property you could be interested in this case is going to be sort of radically non-local. But I can't point to an equation to back that up. So again, luckily none of this is being recorded, right? So I'm fine.
Great, thanks, Tushar.
Thanks, Chris.
Ollie, can you ask your question in half a minute?
Yeah. So it's a plea for clarification. So when you were talking about the Weil representation in response to Neil, I think there was a suggestion that was some kind of many one thing going on, because these pointy representations were meant to be the analogs of PPWs. And now in answer to Chris, again, in the Bohm case, given a wave function, you've got many possible Bohm configurations. So there's again a many one thing going on. Can you say something to make it evident that for a given element of the algebra, abstractly conceived, there's some plurality? Because I'm just not getting an intuitive sense of the sort of many one thing that seems to be presupposed in the answers.
Oh well, so I can represent the algebra as functions on some manifold, but then that's not going to uniquely determine the topology of that manifold. So the same abstract algebra can be realized as the algebra of functions on non-homeomorphic manifolds. So if I want my precisificationally possible worlds to have manifolds, they're going to disagree on topology, and so it'll be many to one in that sense.
Okay, thanks.
Great. With that, we should all maybe unmute and thank Tushar for a really excellent talk.
Thank you very much. This was really a lot of fun. Thanks so much for the questions. And Alex, thanks for the invitation. This is